Hey everybody, in this video we're going to talk about law of sines and cosines. This is section 5.4 and it is how we solve triangles if you don't have a right triangle situation. So how are you able to solve for the missing parts of a triangle, angles or sides, if you don't have a right triangle? So you're not able to use your standard SOHCAHTOA with your sine opposite of hypotenuse. You don't have a hypotenuse anymore. There's no right angles. There's no hypotenuse. So if that's the case, then we have some laws that we're going to be able to use. What you're seeing currently on the screen is the law of sines, and you can go ahead and get those notes down if you want to pause the video. Before we get too deep into the woods on how to solve with these, it's also really important for us to even identify from the beginning which type of law are we going to use. And the way we decide which law we're going to use is 100% based off of if you are working with a triangle where you are given angle, side, or if you're given a triangle where you're given the angle, side, angle. Now, there's also one other case, and we're going to talk about that in a few minutes, where we will use the law of sines. However, these are the two that are most common and the ones where we're going to get the best situation with our answers. So the law of sines, like I said, you can see that on your screen. But before we get too far, I want to practice being able to identify what you're even working with. So I'm going to kind of take it all the way back to geometry for a moment. For anybody who used this type of thing in your geometry class, you might recognize this worksheet. This is from the All Things Algebra curriculum, and depending on your geometry teacher, you may have seen something like this before. But I'm only going to briefly put this on the screen to use to discuss if you know what to know what you're working with. So I can see on my triangle situation here, this is what you would use when you're trying to prove that two triangles were congruent. And it was all based off of what you have. What are you given? So back in geometry, you would have identified that, yes, they have a pair of congruent angles here. These have a pair of congruent angles down here, but they also share a side. And so what you're able to do is you're able to look at one of these triangles and see that, yes, that side is between the two angles. This would be an angle, side, angle situation. And you would have said that they were congruent due to the angle, side, angle theorem. But we're identifying what we're working with the same type of way you did this back in geometry. If I looked at number 2, I want you to look at this. We have a pair of sides that are congruent. We have a pair of sides congruent top and bottom, but we also have the pair that they share. And the sides, so now that I know I have 3 pairs of congruent sides, you know that these were congruent based off of the side property. Or you look at number 3, and we were able to tell this one that these were congruent. Look at the order. I have 2 angles and I have 1 side, but this is different than number 1 was. On number 1, we knew that this was angle, side, angle because the side was between the 2 angles. But this one does not have the side marked between the 2 angles, right? This is not marked. It's this one over here. And if I went in order around the triangle, that's angle, angle, side instead. That is a different situation. Okay. If I look down at, let's kind of skip ahead maybe to one more. This guy, number 7. Y'all look at this one. I see 2 pairs of sides right here, or a pair of sides. I see a pair of angles, and then there's a side that they share. If I look at only half of this, we can see that the angle is between the 2 sides. This is side, angle, side. So the order of these things matters, right? If you looked back at number 1 and number 2, both of them had 2 angles, or number 1 and 3, right? Both of them have 2 angles. Both of them have 1 side, but the order was different, and those were 2 completely different properties. The order does matter, okay, to be able to distinguish which type you're dealing with. So that was just a quick reminder on some of the things that you would have seen in geometry that might help you just a little bit while you're looking through this. All right, we're going to look at section 5.4 back at these problems. And what the law of sines is good for is if you are dealing with a situation with an angle, angle, side, or if you're dealing with an angle, side, angle. Y'all can see in our formula here, what you're going to have is you've got ratios that you're going to set up. And the way we make those ratios is based off of the sides and the angles. The side A, or side A is across the triangle from angle A. So even if I had these as different letters, the ratios still work out the same way because the way this is set up, uppercase A is across from lowercase a. Uppercase B is across from lowercase b. Uppercase C is across from lowercase c. So I'm seeing that we have that kind of matchup. When you set up your proportion, when you set up your ratios, make sure that in one ratio, it's sine of A over little a. Remember, those are across the triangle from each other. Sine of B over little b. Again, those are across the triangle from each other. We want to make sure that we're following that same order. All right. So we're going to get into example 1 here. Example 1 is a situation for law of sines. How do I know that? Because I'm looking at it and I'm seeing angle, angle, and then I'm given this side right over in here as 8. So angle, angle, side, that fits my law of sines. First thing I want us to do is make a note of that. Okay, this is angle, angle, side. This is sines, law of sines. Okay. And then what we're going to do is set up some ratios using that law of sines that you're seeing on the screen. All right, so let's see what I have. Do we see how we have both the angle A and the side A? I can use a ratio that sets up the A's, sine A over little a. Because I know both of those numbers, that is definitely a ratio I want to use. There's also another value we know. We know angle B is 48. So angle B is another value I know, but I do not know side B. And so what I can do is I can make a ratio here that will allow me to find that missing B value. I'm going to plug these numbers in. It might become more clear then. So we're going to say sine of A. This is sine of 36 degrees over lowercase a, 8. That's equal to sine of B, 48 degrees, over side B, which I do not know. So right there's a proportion. We can solve this real quickly just by doing some cross multiplication. We're going to multiply B times sine of 36, 8 times sine of 48. We're going to divide both sides by sine of 36. So B equals 8 sine of 48 divided by sine of 36. And this is the part that we're going to go type into our calculator. So let's talk about the calculators, yeah? When you turn the calculator on, we need to make sure that it says degree up in the top left corner. It should say DEG. If it does not, if it says RAD, then you need to change that setting. So real quick, how to change your setting is go down to the bottom right-hand corner where it says settings. That first option lets you change your angle measure and make sure that you select degrees. And then you should be good to go back to your calculation screen. We're going to type this in exactly how I see it here. So it's going to be 8 sine of 48 and divide that by the sine of 36. And we're going to grab that value. Now, for the sake of trying to be careful with all of our decimals, it's probably in your best interest to, first of all, acknowledge the fact that this is truly a big, long, fat decimal. It's irrational. It's never going to end. But we are on the assignment in here. We're going to be asking to round to the nearest 10th. So we can go ahead and do that. Round to the nearest 10th value, 10.1. Okay. Now here's the thing. I'm not only trying to solve for B. I'm trying to solve the whole triangle. And to solve the whole triangle, I need all of the missing parts. I need all of the measures, all the angles, all the sides. This is not the only thing I was supposed to do. So I am not done. Let's kind of maybe take inventory of what we have and what we still need to accomplish. So I do know angle A, angle B, but I do not know angle C yet. So A was 36 degrees, B is 48 degrees, C is, we don't know yet. We'll get there. Okay, what else do we know? We know some of the side values. Let's see, we've got A was 8. We literally just found B to be 10.1. And we also need to find C. So just trying to take stock of what it is we still need to have completely solved the triangle. I'm still needing angle C and I'm still needing side C. So let's figure that out. How are we going to get angle C or side C? I really need one of the others by doing some other kind of math before I can use law of sines again. If you notice, for C's, those are both in one fraction. And if I don't know either one, I'm not going to be able to solve for the missing. So I need to find one of those values before I can use law of sines again. And I think the easiest thing for us to do is find that angle C. That angle C I can get pretty easily because all of the triangles will always have 180 degrees inside of their angles, if you add up all their angles together. So we can find the measure of angle C if I just take the angle 180 degrees and subtract the two angles that we currently know. Subtract 36 and subtract 48. That right there will give me that angle C is 96. So we can get that. And now that we know angle C, we can do a law of sines to find side C. The exact same way that we did law of sines to find side B, we're going to do the exact same process to find C. So let's do it. All right. We're going to still rely on that relationship that was already known, sine A over little a, and then sine of C this time over little c. And we're going to plug in what we know, solve for what we don't. Sine of 36 degrees over 8 is equal to sine of 96 degrees over c. We're going to cross multiply. We'll solve. We'll have our answer. C times sine of 36 equals 8 times sine of 96. Divide by sine of 36 on both sides, and you will get your C value. This is what we're going to type in our calculator right there. 8 times the sine of 96 divided by the sine of 36. All right, once I typed that in my calculator, it in fact gave me 13.53585367. And that gives me C is to the nearest tenth about 13.5. Okay. All right, so right there, we've solved our first triangle. They asked me to find all of the missing values. We've got them. That was for sure a law of sines question. It was angle, angle, side. Done. Now, there's one other thing that I want to accomplish in this video to talk about law of sines. This is just your typical little law of sines question. When you have angle, angle, side, or an angle, sine, angle, this is kind of the process you're going to go through and find your missing pieces by setting up these proportions. However, what if we have a very special circumstance? Okay, if we have a very special circumstance, I have to try to, I'm going to do my best to draw pictures. I'm not very artistic, but I will do my best. What y'all are going to see is we have this thing called the ambiguous case, side, side, angle. Make sure that you spell this in the proper order. Otherwise, we're going to have something on our paper that we do not want. So please make sure that you do write it um, with your letter in these orders, or letters in this order. But this ambiguous case, side, side, angle, when you have that order, then you're going to have to use the law of sines, just like we talked about doing law of sines a minute ago. But the problem is that for a side-side angle case, you do not only have one potential triangle it could be. If you guys remember back to your geometry class, you were not able to prove two triangles congruent using side-side angle, not just because it spells a bad word backwards, but also because of the fact that it ends up creating two potential triangles. You're not limited to one. I'll do the best I can to draw this out and show you. In class, I have like a poster with like a nice little diagram with this so you can see it a little better, but I can't fit the big fat poster under the camera. So you're just gonna have to do the best you can with trying to follow my picture, okay? So for this ambiguous case, here's what I'm talking about. All right. We have two scenarios. What are the two scenarios? Well, in my situation here, we've said that angle A is 30 degrees. Let's just draw a 30-degree angle. As probably a little bigger than 30, but it's okay. Let's draw a 30-degree angle. All right. We're going to let that be angle A. Now, across from this triangle is going to be side A. Now, I could have this triangle be kind of like this. This is a potential. Across from this would be side A, which is 6. Okay. I'm going to let this side or this angle right here be B, which would leave this piece right here to be a 7. Okay, that's a side B. Then let this one be a C up in here. We don't know little c. Okay, now this is one potential option for what my scenario could be, but it's not the only possible triangle to draw. Another possible triangle would be, okay, I'll probably do that a little bit big. It's okay. What if instead I had a scenario like this? Now, again, my artistry could use some work, right? I am not the best drawer, but it's possible for this to be my 30 degrees. It's possible for this side to be my 6 and that side come in. Side-side angle does not guarantee one triangle. Side-side angle has the potential to be two different ones. So what that means is when you have this situation, you are kind of caught with having to solve for two full triangles. Now, in both scenarios, you have your angle A, angle B, angle C. Angle A is 30. And that's going to be the case for both triangles. I'd find my side A, side B, side C, which again, I know two of those. And for both triangles, these values are for sure the case. But what about the other ones? What about the ones that are unknown here? Angle A is 30, but angle B doesn't have to be the same thing for both triangles. So what we're going to have to do is actually solve for both scenarios. Now, let's set this up. We're going to try to solve it out by just seeing what I can do. Okay? We're going to see what our options are. So for sure, I know angle A and I know side A. And so just like I did in example 1, I want to use that relationship. I want to use the fact that I know those two and set up a ratio between sine A and side A. The other value I know is little b. So I'm going to let this other one be the b's. And let's plug in what we know, solve for what we don't. So I know that we have 30 degrees for A. Okay, down here we're going to plug in a 6. Here we have sine of B over 7. We're going to cross multiply 7 times the sine of 30, which you might know from your unit circle, and then 6 times sine of B. We're going to divide both sides by 6. So 7 sine 30 divided by 6 equals sine of B. All right, now this is honestly one that you could probably do by hand. Depends on how well you know your unit circle. I am going to pop this in the calculator just so we can practice with that as well, because most of the time these numbers are not going to be as doable. So if I type that in, we do end up getting 0.5833, so 3 repeating. And yeah, so I got, and honestly, I may just let that fraction stay. I mean, might as well, right? That fraction's a little better. 7 over 12. Let's stick with that. 7 over 12 equals sine of B. If I do sine inverse on both sides, you will then be able to see what a potential value for B is. If I sine inverse, that will cancel out the sine, which is great. The one issue that I have, when I do this in my calculator, sine inverse, 7 divided by 12, I'm getting 35.68533471 equals B. All right, so I've got angle B, but this is an acute angle. And I want you to look at my two options. B could be acute, but B also could be obtuse. Depends on how that leg is swung, if it's swung in or if it's swung out, right? So in this case, I found the acute value for B, and that would be this one right here, 35.7, if I round to the nearest tenth. But the problem is that's not the only option for B. And you might be saying, what are you talking about? That's what the calculator told me. And while that might be what the calculator told you, it is not the only value. If you can recall from when we talked about our inverse sine can be found by looking at the right side of your circle from negative pi over 2 to positive pi over 2 on the right side of your circle. And this exists on the right side of your circle. But the thing is, it's not the only place where sine is going to be this value, because sine is also going to give you that value at a completely different location. I'm going to draw you guys a little picture over here on this side, okay? I want you to remember back to your circle stuff, okay? Let's think about this angle, 35.7. 35.7 is probably around in here, probably a little smaller. I just can't draw very well. But 35.7 is going to be around in here. But the y value or your sine value will be the same thing if I just look right over in here. If I were to try to consider this obtuse angle, that's going to be the same y value or the same sine value. So what I'm thinking is this measure is 35.7. So to get this obtuse angle, do 180 minus 35.7. So that this angle ends up giving us 144.3. That's your other option for what B could have been. If B was obtuse, that's what B would need to be. So your other option for B is 144.3 degrees. And I'm going to try to fit that in this little spot I gave myself. 144.3. Both are possible. And this is where the problem splits. Now I have to work two completely different solving problems to get my C values. So let's do that. All right, to get my C values, we're going to go with a law of sines once more, but this time I'm going to compare it to my C's. Also, one other thing, I can get that angle C pretty easy now. The measure of angle C is going to be 180 minus 30 minus 35.7. Now, again, I had rounded this, but it's probably safe here to go ahead and let me use this decimal. It'll give me 114.3 degrees. For that C value. I'm going to separate this out a little bit. All right, so that gave me the C value there. So now all I have to do is a law of sines, and I'll have my side C. Okay, we're going to do a law of sines here. I'm going to use sine A over little a equals sine C over little c. Sine A, sine of 30 over 6 equals sine of 114.3 over little c. And we'll keep on solving. Cross multiply. C sine 30 equals 6 sine 114.3. C equals 6 sine of 114.3 divided by sine of 30. And now is where I'm going to go to my calculator and we will get our value here. So these ambiguous cases are a little bit more work because you have basically two triangles you have to solve. Now for this first one, I got that C is going to be 10 point, and I'll go ahead and round it, 10.9-ish. That was my last one to have to find on that triangle, so I'm good there. These are a little bit more tedious because you have to do multiple calculations for multiple scenarios. However, it really is just very procedural. You're able to plug the values into the equations, solve it out, have the answers. So some people really, really like these because they're kind of like that. It's just, this is how you do it. There's not really a whole lot of deeper thinking having to go on with it. But the math can be a little finicky. So it's easy to make little mistakes here and there as well. All right, here I'm going to do my angle C. So I'm going to subtract 30 and that 144. Oops, I ran out of space there. But 144.3. And so I get that my angle C on this one is 5.7 degrees, which is itty bitty, teeny tiny. That's what it is. All right, from there, let's do a law of sines, find our side C, and then we will be done with our law of sines section. So we're going to do sine of A over little a equals sine of C over little c. But this time we're using the values from my second triangle. Sine of 30 over 6 equals sine of 5.7. Oh, that's so little. Over c. We're going to cross multiply. C times sine of 30. These are all degrees. I should keep my degree symbol. Sine of 30 equals, and then we have 6 times sine 5.7. We're going to divide. So I get 6 sine 5.7 degrees divided by sine of 30 degrees. And this will give us our answer right here. Let's see, make sure I've got it typed in my calculator the right way. Oh, that's so itty bitty. All right, this side is 1.2. And that gives me C. All right, so in this video, we were able to get through all of the law of sines things that we needed to talk about. So your law of sines is going to be used. Let's recap really quick. Our law of sines gets used if you are working with angle side or an angle side angle. Those are the two easiest ways to use law of sines. However, law of sines can also be used to do the ambiguous case side angle. Now that one does not come up very often because it's not really something we'll ask you a whole lot about. But do know that in some cases you will be expected to be able to solve and deal with both possible scenarios. Okay, so just make sure that you are aware of that and how that can produce two different triangles. And law of sines is what we use there. And then law of sines we also use for these two cases. All right, that is it for this video. Guys, make sure that you watch part 2 where we're going to talk about the law of cosines as well once I have that posted. As always, good luck, and always feel free to reach out if you ever have any questions. See y'all on the next one. Bye.